So let's try to learn few more aspects of programming. So in this regard, for this particular session, what we plan is try to look at few concepts about library modifications. So one is how to fetch a new library for non-Newtonian models and how to modify some dynamic mesh movement libraries and all these things we try to learn with the help of this session. So in that regard, let's start our discussion with this implementation of some non-Newtonian models. Okay, so when we talk about this non-Newtonian modeling, so normally we in our normal scenario we try to look at the Newtonian fluid. Okay, and for that we know that when we talk about the Newtonian fluid, the shear strain rate is linearly depend on the shear stress. Okay, so that is, and the proportionality constant we say is a constant of proportionality we say is it as a viscosity. Okay, so that is how we can link the shear strain rate and the shear stress with the help of the viscosity. But when we talk about the non-Newtonian fluid, there is so many different variety of non-Newtonian behavior is available, like viscosity is dependent on the time. Okay, another case is a shear thickening fluid and shear thinning fluid, that we all aware about that concept. Okay, so when we talk about that all part, okay, so various type of the non-Newtonian models is emerged. Okay, and if you look at the literature, so many different type of non-Newtonian model is available, like power law model. Okay, where the viscosity is not directly proportional to the shear strain rate. Okay, so but it has a some consistency index, and this shear rate is some power of something like some index. Okay, so like that way it is very simplified way one can look at the power law. In the other few models also available. So all this here I mention only these four, because this four model is coded inside the OpenFOAM. Okay, so that is what already available inside the OpenFOAM. Now first explore what different solver is available inside the OpenFOAM that will support this non-Newtonian modeling. Okay, so if we go to the install area, applications, solver, okay, incompressible. So first basic solver available with us is the simple form. Okay, so if you look at the simple form definition, it says steady state solver for incompressible turbulent flows. It doesn't only restricted towards the Newtonian fluid only. Okay, so we can use this solver for steady state class of calculation. Then if we look at another solver, that is, let's say, piezo solver. Okay, so piezo solver, if you look at, okay, so piezo solver also says that for incompressible class of the flows, but it doesn't restricted towards only for Newtonian fluid. But very sophisticated solver available, that is the non-Newtonian icoform. Okay, so that is another class of the solver available. So transient solver for incompressible laminar flow for a non-Newtonian fluid. So this is a dedicated solver available, okay, inside the OpenFOAM. So this is what one supposed to know, what different class of the solvers is available. Okay, and now when we talk about this Newtonian or non-Newtonian modeling, so normally we rely on some transport models. Okay, so where exactly this transport model is available? So for that we have to go toward the SRC folder. So if you go to SRC folder, inside the SRC folder we will see these transport models. Okay, and inside the transport model we have a various class of different model is available, like two-phase mixture model, two-phase properties of mixture model, then interface property. Okay, then if you look at the incompressible, inside the incompressible we have a two part. One is the transport model. Okay, so if you go toward the transport model, okay, we come to know that it is just giving us the some basic template. Okay, of that, and inside if you look at it, H file, important is this definition of laminar viscosity. Okay, it is defined inside this .h file. Okay, that is available at that area. And then if we go toward the single phase transport model, and if you explore the single phase transport model, okay, so inside of it has a couple of things, like single phase transport model also look at the viscosity models. So viscosity models is give us the different class of the non-Newtonian modeling. Okay, so that's why, and here also you have Newtonian model, and if you look at the Newtonian model, so Newtonian model we can look for the this particular viscosity. Okay, and that viscosity we can immediately define as a nu. Okay, so that is a how it is in the Newtonian modeling. Okay, so above that, if you look at the single phase transport model, okay, so we have this very important line. Okay, so inside the single phase transport model we have this viscosity model PTR. Okay, so and that is coming from this particular model.h file. Okay, so here we give the pointer to this PTR. Okay, so that pointer we define here. Okay, and that we going to use, okay, to quantify the nu. Okay, then we have another is the correction. Okay, so viscosity model and the correction. Okay, so all these things we can based on that two lines. Okay, what normally happen, let's say we go to the power law. Okay, so inside the power law, okay, this calculate nu is going to affect that area. Okay, basically. Okay, so that is how one from another file is linked. Okay, so that is this is the corrections. Okay, so viscosity model PTR correction files, and nu it is the let's say member function of this particular single viscosity model sub abstract class or subclass. Okay, so and it coming from this area. So if you go towards that viscosity models, okay, so we come to know what that part. Okay, so viscosity models. Okay, so inside the viscosity models we have this entry. Okay, so yeah, here. Okay, this, and the strain rate is also part of viscosity model. So strain rate, how the strain rate is calculated. Okay, if you want to understand, it is available here. Okay, so strain rate is if you look at the definition of strain rate, is something like this way. Strain rate square root of 2 times symmetric gradient u, and symmetric gradient u is nothing but gradient of u plus gradient of u dot transpose. Okay, and symmetric gradient u. So with the help of that we can quantify the strain rate. Okay, so the strain rate is also the part of the viscosity models. Okay, so all are the functions that is defined inside the viscosity models. So with the help of this one line we can take that entries in line with the any of the Newtonian or non-Newtonian modeling. Okay, so that is how one after another all the properties is linked inside the any of the solver. Okay, so that is the few things one is supposed to know. Okay, and if you go towards, let's say, power law and .c file. Okay, so inside the power law, okay, here calculate nu. Okay, so calculate nu allow us to calculate the this viscosity. Okay, so that is how it is linked inside of it. Okay, then if we go towards understanding of few more aspect. Okay, so one thing is that all the non-Newtonian models is coded inside the viscosity model here. Okay, now our aim is to model a new non-Newtonian model. So our aim is to, let's say, model some Casson model. Okay, so that is a well proven model inside the non-Newtonian behavior. So how to code this very simple model and how to use that, so we try to understand that concept. Okay, with the help of this particular session. Okay, so for that let's try to adapt any of the non-Newtonian models. So let's start with this. Okay, so before that let's try to go towards the coding part. Okay, and inside the coding, let's say we are talking about non-Newtonian modeling. Okay, so let me say his name as a non-Newtonian model. Okay, and inside of this we can have a one more directory, okay, 001. Okay, inside of it non-Newtonian, but I don't want any space in my directory structure. Okay, so here we have a model, in between model we have a space, so let's first remove that space. That's fine. Inside of it we want to construct this Casson as a model. Okay, so let's give the same name inside of our this directory. Okay, so we are set with this. Now let's adapt any of the file. So let's say start with this power law. Okay, keep the power law inside of it. Okay, now for compilation what we require the make file. So search for make file, so it is available. Just copy from this area to this area. Okay, so from where I copied, so if you look incompressible viscosity model, I pick up the power law from here. Here no any make file, so just come out of that folder, you will see the make file, straight away copy into your area. And now let's open both the file and have an idea. Okay, first let me clean all these things. Okay, so here I don't require any of these things. Okay, so let me delete that. Fine. Okay, and I want this as a name of new library. Okay, so I'm copying that name. I supposed to also change the name of that C file as well. So Casson model.c. okay, and here lib I say Casson model, that is the library name I am using. Okay, so make sure this name is also goes to the .c file. Okay, so with this we are set here. Let's change the name, same way .h file name also change. Okay, so first make sure that we are set with the environment. Okay, now open this. So in case of the power law, Control H, Control V, so everywhere change the name, same way in the C file and H file. Okay, so first we ready with the template, then we start modifying based on our requirement. Okay, so let's go to the area. Okay, let's say OF 3.0x, okay, wclean dot all. Okay, so wmac, and it's supposed to be dynamically linkable library, so libso. Okay, so viscosity model.h file is undefined. Okay, so we have to set a proper path so that we able to get that particular file in line. So if you look at here, we don't have a proper understanding about the transport models. So how to fix that? We know that whatever the models is using the transport model, that means if you go to the application incompressible solver incompressible area, let's say non-Newtonian. Okay, so whatever the way they are accessing this transport model, if we fix this, okay, I think we are fixed with this requirement. Okay, so let's fix that two line from this area. Along with that, maybe this incompressible transport model, that lib file is required, so let me fix that. Okay, finite volume, let it be there, and mesh, I think mesh is not required. If we give the error, then we think. Okay, okay, so till it's not able to find out the this viscosity model.h file. Okay, so we have to find out from the src folder where that exactly the file is located, and then we give that path to that. So go to the transport area, transport property, transport model. Okay, let's say incompressible ln include has this file. Okay, so if I incompressible and if I use this name as a ln include name, I able to fix that part. Okay, so I say that let me put it like this way and use this. Okay, then let's say ln include we want. Okay, so with this we able to manage the dependency. It now able to see this file. Okay, viscosity model.h file. Okay, what else? Okay, cannot open some, yeah, that is correct, because inside the file it is lib, so we supposed to say user lib bin.so. Right, so with this we are set with this library creation. Okay, so our library oblique, that means our template is ready to go. So what I did a very simple thing. First I went to transport models. Okay, find out where it is, where this non-Newtonian model is available. So it is available in the transport modeling, incompressible, viscosity models. So I pick up any of this. You can pick up any one, not an issue. So I pick up that, copied inside of this area. Okay, and then okay, I think I can take this part out, that is better. Cut, because I have multiple directories, I don't want that way. Let me delete this and again recompile that as well. That is fine now. Okay, so with this we are set. Okay, so I first copied that particular files. Okay, this two file, rename it to Casson model.cn.h, find out the Mac folder most near to our area. So this is the Mac folder, and then we have to resolve the dependency. So for that we add up the few lines from the solvers, but after that also it giving us this error. Okay, viscosity model.h file is not visible. So explicitly to fix that, what we did, we try to copied few lines. Okay, so we try to fix by including this transport model income ln include file. So normally all that file is available at the ln include level. Okay, so if we have this, we are set with our requirement. Okay, so we set this one library. Okay, so that means our environment is ready to go. Now let's try to code for our requirement. So if you look at here, we have a nu is nothing, square root of nu is nothing but the tau y by mu is yield stress, and unit is meter square per second square. Okay, and nu is the viscosity, and gamma dot is the shear strain rate. Okay, and m is the consistency index, and its unit is meter square per second. Okay, so now we want to code this entry inside of our area. So that is what we're going to do. So for that our template is ready. Now we require certain modification inside of this particular file. So before we go towards that modification, also try to understand how different this viscosity models is coded. So if you look at here, we have a different, let's say power law. Okay, is nothing but eta k is consistency index into strain rate power of n minus 1. Okay, so if you want to look at how it is coded, open this both the files. Okay, inside the this C files. Okay, inside the wherever you have a calculate new, that is the main part, and in there it is coded something like this way. Okay, so it is min max we are sometime giving to limit the minimum and maximum value of the new. Okay, it is sometime required to avoid the singularity during the calculation of dynamic viscosity. Okay, so that is why we, even though if you look at the explicit equation, none of the places this min max value is available. When we look at actual implementation, okay, so if I, let's say, so let me open that file again. I want to use like this way, and yeah, so if you look at exactly okay. So if you look at here, k into power of the strain rate. Okay, so here is the strain rate. Okay, and we are using this 1 as a dimension. Okay, and strain rate and dimension small is, so what we exactly what we are doing, we are taking this strain rate, okay, but we are fixing some small value. Small value is very tiny value. It allows us to always make sure that this strain rate is never be in the negative side. Okay, and so this is nothing but maximum of this strain rate and power of this index, okay, n minus 1, okay, and k into power of this. So from here we always make sure whatever the strain rate is we are getting is always be a positive inside. Okay, so that is why we have this small value dimensionless, and with the help of that we are able to fix this particular entry. Okay, so it's very simple way to look at that particular code. Okay, so now in the similar line, if you look at the code for, let's say, cross power law. Okay, so for the cross power law, if you look at the .c file, this is the how we are calculating this particular file. And if you look at the equations, okay, this is the equation for cross power law. Okay, for that we have a nu equal to nothing but nu 0 minus nu infinity divided by 1 minus some power of m into strain rate, okay, plus n infinity. Okay, so this is very simplified way we can easily compare the our lines of code whatever is available inside of it. Okay, and then if we look at the another models, okay, so let's say go to this models, okay, and try to compare the nu calculation files. So it gives us the idea how to code it. Okay, basically, so that is third model. So here tau 0 underscore is nothing but sum of the constant, okay, yield stress. It is coming from the user interface. Okay, and then k, then we say this one. Okay, so strain rate, so nu 0, okay, minimum of either we limit, okay, some minimum and maximum. Based on that we are basically using this. Okay, and this term is to fix the only dimensions. Look here, its value is 1 only, but to if our dimension is not matching, then how to fix? We artificially construct some dimensions. Okay, so dimension scalars, and these both are just the one value, but to fix the dimension inside the our equation. So sometime we have to play with this class of the some of the artificial variable creation and to fix the dimensions. Okay, so without this it may compile, okay, but when you execute, when you exactly run, it will show you some error because our dimension is mismatched. So to fix that we are doing this. Okay, so this is nothing but for the dimension point of view we are using this. Okay, shear strain rate. Okay, now fine. So SR we able to quantify like this way. Okay, and SR is nothing but the we fix here as a shear strain rate. Okay, so because multiple time if we want to use it, so that's why we are using like that way. Okay, then this is another model where also we can see check few more entries. Okay, so let me open with this our normal, this is the calculate of it. Okay, so look at how it is coded. Okay, so nu infinity, okay, so nu infinity 0 infinity into power of some scalar value. Okay, 1 plus, okay, so I think here this is supposed to be power of this, that's why it is look different way. Okay, so here also this lower bound viscosity and upper bound viscosity, okay, and time one of the constant. So like that way we can quickly adapt any of the formulas. So now in the similar line, let's say we want to code this. Okay, so if you want to code this, so first part we are set, we able to manage the our new template. Okay, now with that template, let's try to code our new libraries. So for that, let me first close everything. Okay, let's go to our programming area, code. Okay, now this is the our models what we are using. Okay, non-Newtonian, but I want name here, so that is, I think, better way to look at the model. Okay, so what I do, I try to construct this name. Okay, again reverting back. Now that is better. Let me do that. Okay, so we are set with this template library. Now we have to code this one equations. Okay, so let's do that and fix the our requirement. Okay, so if you look at what different thing we required, one thing we required is this m as a one constant, and another is tau y is yield shear stress. Okay, so these two things we have to ask from the user. Okay, so that is what we needed here. So let me first start with this. So two things is needed from the user side, and then if we want to look at few more entries like new min and new max to limit the values, so that is normally people do. So in that regard, if we go with that, then we have a new min max, that is fine. Okay, along with that I required so normally when you want to modify anything, okay, so don't first delete anything. It's better to first construct new variables. Okay, so I say, let's say we required two new variables. Okay, one variables is for, let's say, m, which one, this one. For m we require new variables, so first construct the new variable as a m underscore, and then we require new variable for this tau y. Okay, so I gave this new variable as a, again the dimension scalar only, tau 0 underscore. Okay, so this two variable we constructed as a dimension scalar. So when you construct this two variable, okay, what else change required here? Nothing. Okay, so we able to fix this two variable inside the .c file. So first also fix this variable as a its constructor inside this file. Okay, so here no change. Here later on we modified. First let's construct this new two variable also. Okay, so for that let try to fix these two variables, okay, as a constructor as well. So but we don't want to delete anything. Okay, so we let it be the available whatever we have. Okay, but in case of that we try to incorporate few more variables. Okay, so now what we required like similar line, it is looking for m and looking for this k variables. Okay, so let's say dim viscosity. Okay, so we want to take the all the dimensions. Okay, so let's say look for a variables, that is perfectly all right. Okay, but we want the dimension to be fixed from the our control dict file only. Okay, I don't want to fix the dimension by dimension of viscosity or dimension less or anything. Okay, so in case other than that, so let me check in one other which area I can find out the better way to write that entries. So let me check here. Okay, so here also they are taking the values from that way. Okay, but I want if we able to take straight away the end value. Okay, so dimension of viscosity, okay. In case of that, if we try to adapt something like straight away looking at the coefficient, okay, and add up the value. So let me check few more if I able to manage in other of the places. So what I'm looking at, I want a very simplified way to read that particular dimensions. Okay, so dimension something like look up type of the things. Okay, so let me go to that particular area where in this, okay, cd, okay, grep minus r, and this lookup is normally the command. Okay, so lookup dot lookup, yeah, it is available in, so IWN, so give me the line number. So it is available, okay, available in the .c file at that locations. Okay, inside of when we are reading at that time it is available. So here in the construction and here is in the reading. Okay, so here it's directly available from where it is reading it. Okay, that is fine. Okay, so why I cannot use same way here? Okay, so if I directly use same way here, that is I think better way to directly fix these values. Okay, so let's do it something like this way in the similar line, like we are reading this. So what I want in the similar line from this area, let's say read for Casson model. Okay, maybe we get some error, but no worry, we able to fix it. Okay, I want some different way of reading this. Okay, I said that I want straight away by this way. Okay, so maybe I require this box, that's it. So you mean you max, that is fine. Same way I supposed to read straight away. Okay, so I don't want to fix the dimension here. Okay, basically, so I want to fix the straight away this entry. Okay, and if it is give some error, then we think to how to modify it. Okay, but now in the similar line we supposed to take this two value also. Okay, so let's me also adapt this as well. So let's say m and look for m. Similar line, let's say what name we gave the name as a tau 0. So also look for tau 0. Okay, C will be fine. So we set here, and reading wise also in the similar line, let's read for m. Okay, and also for our this new member as a tau 0. Okay, and we are keeping over there. So I think with this our constructor and the read member functions is ready. So what it's supposed to do, try to read all the coefficients from the transport property files. Okay, and here we are constructing that all the required variables. Okay, that is normally we use. Now let's look at either we are getting any error or it's fine. Okay, so it's don't like that way. Initialize after no, this is fine. M initialize here. After that, what is it saying? M is initialize after that, that is fine. Okay, tau look for tau. Where is the error? Error is on the line number 90 here. Why we have error of tau? But it says that does not have any field name TAU0. Why it is there TAU0? Okay, it has a double, that's why. Correct. Okay, so what it says that warning will be initialized after all this thing nu max m. It doesn't give the error for tau and anything. Nu max and nu max. Okay, says that it initializes afterwards. Nu max this, fine. So where in the line number 67 warning will be initialized after dimension scalar nu max 67. Okay, this place we are using nu max, that is correct, but why it's supposed to give the error? It's not error, but it is a warning. Dimension scalar m in the line number H64, line number H67. 67 64 says that initialize dimension scalar warning will be initialized after nu max. Okay, order maybe, but how it supposed to affect? Our order is like this way. Okay, nu max m and tau. So how is the order here? Nu max control x. Okay, tau, but how it affect? I have no idea. Okay, so that order is failing, nothing else. Fine. It says that this is defined later on. Okay, and here we are reading it first, so that's why it's giving us the warning, nothing else. Okay, fine. So this is the proper way to read the variables. So we able to set the reading part of the variables. Okay, now we just have to change the our exact functions. Okay, so if we look at here, we have a min max already. So nu min, so we return the maximum value of nu min and all these entries, that is fine. And here minimum of nu max, and we say now modified based on our requirement. Okay, so if you look at the equations, we says that square root, so power of everything. So that's why we have to look at some different function. Minimum here, let's say power of, we first define power of, okay, and power of what to what up to here, and we say comma and scalar 2, scalar 2. So what we define is something like this way. Okay, so what I did is that I first defined this power of everything. So power of everything, power of 2 of this everything. Okay, so that is why I say here. Now inside of it, what we have, inside of it we have a power of this quantity. So let's fix that entry. Inside of it we say, let's say power of this value. Okay, which value? power of some quantity, we say. Okay, so power of what we have a tau y. Okay, so tau y, and then we have a divided by, we have this strain rate. Okay, so that is what we have. So tau y, we define tau y as a tau 0. Okay, so we say, let's say control C, power of tau y divided by, okay, we have a strain rate, but when something goes as a dividations, okay, so always it's better to use this particular smaller tiny value. So we say that max of strain rate, okay, and then we say that something like this way, divided by, okay, so we want to say that divide by what we want here, we want max of some value, so divide by, we say we kept it this way, divide by maximum of, now the dimension setting not required, so we say strain rate, okay, and dimension of, very small dimension of here small value, but our dimension is something like dimensionless and strain rate. Okay, so divided by something like time. I know the dimension, so I am straight away fixing this entries. Okay, so small, and this, in case of the dimensionless, we say dimensionless divided by something like dimension of time. Okay, and with the help of that we fix this entry. So we said tau, power of tau, what we did is power of tau, and what is its power? Its power, so here it's done. Okay, and what is its power? Power of, how much is the power? 0.5. Okay, so this is entry we set. So with this, what we want plus of power of, now straight away we write, then also fine, because it's very simple value, m comma power of 0.5. okay, so we are set with this entries. I think we have to check with the, so mean. Okay, so we're going to return this max of this value, fine, then max of either this or whatever we're going to get out of it, and here inside again we say minimum of either maximum of u, or we can fix this power of tau 0 divided by strain rate, and its power is 0.5 plus of m power of this and scalar of this too. I think it's perfectly all right. Let me check. So with this we are set with the our new model that we incorporate this Casson model. Okay, now what is the additional variable we have? Try to skip that variable. So start from here. We are not using this index, so let me delete that index part. Okay, so k and n I am not using. Okay, so we also get rid of this k and n part, fine, k and n not required. So I think we are ready with the our new developed library. So we set with this lib Casson model dot so file. Now we want to use this particular model. So how to use that? For that we require the tutorial. So go to the tutorial area. Let's fix incompressible non-Newtonian, let's say offset cylinder, whatever is this tutorial, we try to use this tutorial. Okay, go to the test case folder 001. Okay, inside of it paste. Okay, new tab, let it be like this way, code, so I am using this name. Okay, so tutorial number 1 for this name, rename it. Okay, so we are set with this. First let's run it as it is. Okay, OF 3.0, yes, fine. Okay, so non-Newtonian, it's working, and let's check it's using Casson power law. In case of that, let me use our new developed model. So in here we are using this. In case of this, let's use our new model. So which model we use? Casson model. Okay, so we are using this model. Okay, so we require the coefficient also for that model. So we say Casson model coefficient. So that is how one can fix the coefficient as well. And inside the coefficient, what value we needed, we have to check this whatever we are looking. So we're looking for nu min, nu max, m, and this tau 0. So this 4 value we supposed to incorporate inside of it, this Casson model. Okay, so we say that nu min max of some value. Okay, so nu min. Okay, so we say nu min, nu max, it is maximum value. Okay, then m has some value, and then we require the tau has some value. This values we required. Okay, right now I'm fixing the value randomly. Okay, so if we let me check if I have proper value for this. Okay, I have some value. So m is supposed to be unit is meter square per second first of all. Okay, so let me first fix this, everything same locations, fine. So value unit is meter square per second. Okay, so we are set with that unit. Okay, each one has a, and then tau 0 has a unit of meter square per second square. Okay, so we fix with the unit. Okay, mean value, something like very tiny value we fix. Okay, maximum value not more than some 1000 or 100. Okay, m as a index we have a 00414. So I am adapting this value from some of the papers. Okay, and then tau 0 we have a 0.0038. Okay, so that is the value we have, and we are able to read this. Now let's try to use this particular, but it not allow us to do that because this is library we yet to fix as a file inside the control dict folder. Okay, so let's try to fix this error. So for that we have to add one line inside the control dict file. That's it, nothing any difficult task. So what we adapt, we supposed to adapt from our previous tutorial. Okay, so let's say we go towards our programming, or let's say go towards our advanced module, and this last session where we fix dynamically linkable library inside the control dict file. So we have to use libs this command, that's it. And which library we have to fix, that is we supposed to fix this library. Okay, so with this library name, if we specify in the control dict file, that means that that library is in line with our solver. Okay, so with this, if we try to now run, okay, so now something is wrong at found line number 22. Some of the token is missing, where in the transport property file. So let's see, transport property file, line number 23. That is true. I think we required something like this way. So that is the style. Maybe it's needed, nothing else. Keyword is undefined. Okay, so that is coming from our code area. Maybe we didn't set the variable, reading variable properly. Okay, yeah, so look for this variable, okay, here. So this is the problem. We're supposed to set for tau only. So then we change the code, so we have to recompile it again. So few of the error maybe it is observed during the runtime only. Okay, so accordingly we have to tune that. Okay, so now it's working, but how we know it's working with that model? It is mentioned here, Casson model is used. So like that way one can quickly check that either our code is able to pick up the model or not. So let me see the output, how it's look like. So if you want to really test this particular case, okay, so I suggest look at the flow through a channel. Okay, and with the flow through a channel you try to solve for a Newtonian fluid and non-Newtonian fluid, and you will observe that parabolic and not exactly the peak value matching the 1.5 times of the mean value. So that type of modification you will see when you run with this new library. Okay, so I suggest establish a one test case, flow through a channel or flow through a pipe. Okay, because where we know that in the laminar zone, when we look at the flow Newtonian fluid, we definitely look at the parabolic profile with the peak is 1.5 times of the mean value. But when we work with this non-Newtonian model, maybe you will not see the same peak. Okay, so it is the testing of this non-Newtonian modeling. Okay, so this is very simple way to incorporate this non-Newtonian model inside of our new library. Okay, so for that what we did, we first take the template out of the src folder, and then first without modifying anything we just compile it. Okay, and then we while compilation maybe we have to resolve the option file in the make folder to resolve the dependency. Okay, then we, after resolving dependency, our template is ready to go, and then we start developing a new code inside of it. And when you want to start new development, don't do at a time. First, don't remove anything. First only establish a new variable, whatever you think it is needed for your calculations. Okay, and then finish in .h file and in the .c file. Okay, and again compile. Then you establish or develop a code, whatever you want to exactly code it. Okay, and then again compile. Everything went fine. Then whatever is the not used variable, then later on you delete that variable, and then we are set with the library. And for the running the case, what we supposed to do, we supposed to change the name inside the transport model, and also to use this dynamically linkable library, we have to give the name to that library inside the control dict file. That's it. With the help of that we are able to manage the solution with the help of the new developed non-Newtonian model.